Greetings, physics enthusiasts. Welcome to AP Physics 1, where we are talking about sound. And sound is not specifically part of one of the numbered units in AP Physics 1, because I usually teach this lesson after the AP exam. So I'm calling this AP Physics 1, the unit on sound, lesson 1. So we're going to talk about sound, which is very exciting. You know, most of us hear things off and on all day long, whether or not we pay attention. And sound is a great example of some things that we learned in previous units. So sound travels as a wave. So I want to remind you what we learned when we talked about waves previously. Specifically, sound is a longitudinal wave. Sound is a longitudinal wave. And I showed you a slinky like this. It's kind of hard to see in this video. But I showed you a slinky in a previous video. And so let's use it again. I can stretch the slinky like this. And if I stretch it a little tighter, and don't drop it, if I let go of just a couple of coils over here on the left side, I've created a longitudinal wave. Oh, let's do that again. So right now we have a longitudinal wave going back and forth and back and forth. We'll let it stop vibrating. And I just, now as the energy goes from left over here across to the right, there is no piece of metal, there is not a single atom of metal that goes all the way from here across to here. The thing that propagates or travels, except right then, the thing that propagates or travels is not the metal. The thing that propagates is the energy. What happens to an individual piece of metal in this situation? I want it to stay a little bit stretched. I didn't think about that part. So stay a little bit stretched. Let me attach it to the end of the paper. I'm going to make this do what I want it to. There we go. And over here. All right, now my slinky is affixed. So the energy travels through the slinky. But it's important to know that these pieces of metal that are here never make it over to the other end. In fact, these individual little pieces of metal just vibrate back and forth. First, this one vibrates, then it pushes this one, 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 then it pushes this one. And when I did this with a much longer slinky, you could even see that they got a little close together, and then they got farther apart as these got close together, and they got farther apart as these got closer together, and they got farther apart as these got closer together. And so what we have is these compression regions, and the region of compression moves along. And so that's called a longitudinal wave. And I think of the word longitudinal as sounding like along. So the motion of these individual coils is back and forth this way. And the propagation is also this way. So the motion and the propagation are parallel. That is the definition of a longitudinal wave. Now, how does that relate to sound? Sound travels through air, and air is made up of lots and lots and lots of little air particles that, you know, look kind of like this. And the idea that I'm trying to express here is that the air particles are roughly evenly spaced. You know, here, 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 the spacing is roughly equal. When sound is traveling through air, if I were to have, let's just try to do this roughly equally. Okay, that looks roughly equally. As sound travels through air, there are regions where the particles are smushed together and then spread apart. And then a certain distance away, we have more particles smushed together and then spread apart and then smushed together. So if I were to send one little pulse through here, they'd be smushed together, then smushed together, then smushed together. As a pulse goes. So this would be the first pulse going through. This would be the second pulse following it. This would be the third. And let's have them go to the other direction. They would just travel along like that. So if I just go, bam, then just one of these little pulses would be traveling through the room and it would get to you. But if I had more of a continuous sound like this, well, then there's a constant flow of energy with several little crests followed by troughs, followed by crests, followed by troughs. And this would be called my wavelength. The distance between these crests. And that would be the same as this distance. Also lambda, the wavelength. Now, what is it that makes this a longitudinal wave is that these little particles, this one's not moving right now, but the particles move back and forth this way. So these particles have been squished together and they're gonna relax and go back where they came from. And the direction of propagation is this way, and those directions are parallel. And that is the definition of a longitudinal wave. The other kind of wave that we talked about was if I sent a pulse that way. And then in that situation, this is the direction of propagation, but the particles aren't going back and forth parallel to that. They went back and forth perpendicular to that. All right, so that is what happens with the air particles in the room when sound travels through the air. They move back and forth and they have these little compression regions and these rarefied regions. Now, you might be wondering, how fast does sound travel? So let's talk about, the next topic is the speed of sound. Topic 1, sound is a wave. What kind of wave? Longitudinal. Topic 2 for today, how fast does that sound travel? Now, there was a time, in the history of human thought, that they thought sound traveled infinitely fast. The moment I opened my mouth and made a sound, that sound was interpreted by your ear. Not so. In fact, it takes time for the sound to get from me to you. We just don't notice that it takes time because sound does travel pretty darn fast. Lickety split. But not infinitely fast. So where might you have experienced this? I think maybe the first time I ever noticed this was when I was playing golf with my grandparents. And you tee off and then you make your way down the fairway. And if you're good, it only takes you a couple of strokes. And if you're me, it takes you 5 or 10 and you get to the green. And I remember being on the green, noticing that people were back at the tee, starting the same hole that I was on. And I remember looking back and I watched them swing their club and hit the ball. But then a moment later, maybe a half a second, I heard the crack of the club hitting the ball. I saw the club hit the ball, but then a moment later, I heard the crack. I could tell that it took time for that sound to travel to me. Another place where I've noticed this is at the Hollywood Bowl. And sometimes at the Hollywood Bowl, there is an orchestra playing. And a fun instrument in the orchestra is the cymbals, where they bang these things together. And when I sit way far back in the Hollywood Bowl, because those seats are more affordable, when I sit way back in a Hollywood Bowl, I can see the percussionist bring the cymbals together. But again, it's a moment later, maybe a half a second later, before I hear that. So there are times when you see something and then you hear it. I bet if you've ever gone to a Dodgers game and sat far, far, far away from where the person hits the ball, that you might see the swing and then a moment later hear the crack of the bat hitting the ball. Try to think of other examples where you see something happen before you hear it happen. Now, a good number to know is 340 meters per second. That is a pretty average speed of sound here on Earth at sea level in air. And so because I said all those qualifiers, maybe that's giving you a hint that in different situations, the speed of sound might be different, might be faster than that, might be slower than that. But this is, right around here where we live at the surface of Earth, not like here in California, but here on the surface of Earth. The speed of sound is about 340 meters per second. A lot of people just know that. So why don't you memorize that? But let me show you a couple of equations that might be handy for speed of sound. The speed of sound, the speed of any wave is equal to its wavelength times its frequency. We have studied that before. But for sound, there is this equation, the square root of beta over rho. So it turns out, I'm going to put a little arrow up here. The medium determines the speed. That is a great sentence. It's worth putting an asterisk by in your notes, because I know you write down everything I say, or highlighting it. What does that mean? It means that the sound here in my classroom determines the speed. I said the sound in my classroom. The air here in my classroom determines the speed that sound will travel through it. And there's different things that could change about the air that would change the speed. For example, temperature. The speed of sound in air is pretty close to, this is an approximate equation, approximately equal to 331 1 plus T over 273. And that's for the temperature in Celsius or centigrade. In other words, if it were to get hotter in my classroom, we're on a heat wave, it's 90 degrees in here. Well, that would lead to a faster speed than right now, if it's, and of course, 90 degrees is not in Celsius. So let's say a really hot day in the metric system in Celsius is about 30 degrees. That is really hot. It's a hot day. So let's see how fast sound would travel. If we're at 30 Celsius, 30, divide that by 273, add 1, take the square root, and multiply by 331. And we got 349. That's a little faster than 340. That's a really, really hot day. What if it's a colder day and as T gets smaller, V should get smaller? Let's say, it's going to snow. Well, that's 0 degrees Celsius, right? And so that math is a whole lot easier because the square root of 1 is 1 and 1 times 331 is 331. So from really, really cold, freezing, literally, up to really, really hot, 30 Celsius, the temperature could range from 331 all the way up to 349. Now, how is that an example of the medium determining the speed? The air has properties, and one of the air's properties is its temperature. And so hot air is a different medium than cold air. So the medium and its properties, like air, determine the speed. Now, there's other things that are relevant. For example, this rho right here, the Greek letter rho, has to do with the density of the air. And maybe you know it, maybe you don't, but at higher elevations, the air is less dense. So if the denominator here is small, that might tend to make the speed faster. But then there's also this beta, which has to do with elasticity. Elasticity, and rho has to do with density. The only thing you really need to know about this is that speed depends on the properties of the medium. And then there's this specific equation having to do with how the temperature of that medium affects the speed. So sound, in general, travels at about 340 though. If they don't tell you anything else about the medium and they tell you, hey, sound is traveling in air, you could just use 340. Some books say, 343, but rounded to 2 sig figs, rounded to 2 sig figs, that is 340. Now let's talk a little bit about some vocabulary. So something that travels at the speed of sound is sound. Well, what travels slower than sound? I do. So, I'm going to go to a track meet and I'm going to be really inspired by watching all of these fast people. So then I'm going to go home and I'm going to run. And I'm going to run so fast, I'm going to go, 8 meters per second, which is really fast. But 8 meters per second is slower than 340. So I'm going slower than sound. So this is called, there's a word for all the speeds that are slower than sound. Subsonic. Sonic means having to do with sound, sub meaning less than. Now, there are some jet planes out there that travel really, really fast, faster than sound, which is mind-blowing. But so let's say there is a jet that is traveling 360 meters per second, which you will recall is more than 340. So it's traveling faster than sound, and anything that travels faster than sound gets an adjective, and that is supersonic. Sonic meaning having to do with sound, and super meaning more than. So I don't know why we don't have, subplat and superplat describing speeds of people who run slower and faster than me, but we do have adjectives that describe things that move less fast than sound and faster than sound. And so those are those adjectives. Make sure that you pay attention to them because we're going to learn a couple more adjectives really soon that people often accidentally use instead of these. They get them mixed up. So let's not get things mixed up. So one of the main characteristics that we talk about, well, there are two. I'm going to tell you the two things that we talk about the most when we talk about a sound, and we try to characterize that sound. We try to describe that sound, is how loud it is, which we'll talk about in the next video, and how high or low that sound is. And that high or lowness of the sound is called pitch. So if we're playing the piano, there's the high notes and there's the low notes. If you're playing any musical instrument, or if you're singing, or even if you're talking, you can change your pitch. And pitch is related to frequency. In fact, pitch and frequency are often used as synonyms. And when we think about frequency, there it was in that equation. Wave speed is wavelength times frequency. So there's the wavelength. And pitch has to do with frequency. the number of vibrations per second. So it turns out that the human ear can hear some sounds and it cannot hear others. Have you ever seen something that people call a dog whistle, you know, and it looks like you're blowing into it, but you're like, I don't hear anything. But then your dogs go crazy because it's so high pitched that we can't hear it. There are sounds that are of frequencies that this piece of lab equipment just does not detect. Interesting. Turns out the lowest pitch that humans can hear is around 20 hertz, 20 vibrations per second. Still sounds like a lot of vibrations each second, 20. And the highest pitch that humans can hear is more like 20,000 hertz. So this is called the range of human hearing. Can there be longitudinal waves in the air that we call sound? Can there be those waves that are 10 vibrations per second? Absolutely. Are there animals on the planet that can hear them? Yes, there are. Are humans some of those animals? Nope. Are there vibrations that create waves that travel as sound through the air that are 22,000 hertz, 22,000 vibrations per second? Yes, there are. Are there animals on the planet that can detect those waves? Probably. Are humans among those animals? No. So this right here is a lot more about biology and you know, paying attention to us than it is about physics. But so these listening devices can only detect frequencies from about 20 to about 20,000 hertz. As you get older, this range shrinks. So if you have a phone and you Google a little app that makes a mosquito sound, it just makes your phone make this really, really high, annoying pitched sound. But if you play it around old people like me and your grandparents, we might not know that you're playing it. I can't hear those high pitches because I'm old and my range of hearing has shrunk. So that might be a fun experiment for you. Go to the App Store, download some free app, don't spend money. The mosquito sound or the mosquito ringtone, they tend to call it. And some of them even allow you to dial in what frequency you want. And that could be a fun thing to compare with your friends. You know, who can hear 20,000 hertz? Who can hear 19,000 hertz? Who can hear 18,000 hertz? Who can hear 17,000 hertz? And so on. But there's the range of human hearing. Now, if a sound is too low pitched for humans to hear it, we have an adjective for that. Still a sound, but it's too low to be heard. We call that infrasonic. Sonic meaning having to do with sound, infra meaning less than. Not less fast, no. Smaller frequency. Now you see why I told you these words. And if something is too high pitched for you to hear it, then we call that ultrasonic. And so something that is ultrasonic for me that I can't hear might not be ultrasonic for you. And then of course, something that we can hear, we call audible, meaning able to be audiated or heard. So adjectives. Infrasonic and ultrasonic. Infra and ultra are prefixes that mean less and more. Sub and super are also prefixes that mean less and more. But these adjectives have to do with frequency or pitch. And these adjectives have to do with speed. All right, so I wanted to put those all on the same page so that you could distinguish them from one another. Okay, now I just want to show you a brief demonstration and I have to reach to grab my thing. So I'm going to put this on pause for a second. So the last thing I want to talk to you about today is called natural frequency. Some things, when you set them in motion, vibrate at a given frequency. For example, we studied this in the last chapter. We said a pendulum has a period of 2 pi root L over G, which means its frequency, which is the reciprocal of the period, is 1 over 2 pi root G over L. In other words, every pendulum with length L has this frequency F. So every time you push something that's that long, it's going to vibrate back and forth with that same frequency. Interesting. It's the length that determines the frequency. We also said for if we put a block on the end of our spring, we said the period is 2 pi root M over K. Does that sound familiar? And therefore, the frequency of a block spring system is 1 over 2 pi root K over M. So again, this depends on this only depended on one factor, the length. This depends on 2 factors, both the stiffness of the spring and the mass of the object that you attach on the end. But the frequency is called the natural frequency. The natural frequency of an oscillator. Natural frequency of a pendulum, F sub P for pendulum, natural frequency of some spring system. And a lot of things in the world have a natural frequency. I remember I noticed when I was a kid, if I tapped on a water glass, tapping on my coffee mug or my tea mug doesn't really do anything. But tapping on some things, they will vibrate with a certain frequency, and you can tell that because it's it's singing or a note or making a sound of some pitch. So here I have a tuning fork, and I can tap on this tuning fork and it will vibrate and we will hear a note. Let's see if you can hear that. Can you hear that? Maybe I'll bring it. I'm actually not sure what microphone my computer's using right now. So, where is the microphone? I should know that. I don't. I think it's on what microphone we're using. So I'm just moving this around to different places. But I hit it. Now, I hit it with something soft here. And it's making that note. And I hit it again. Hopefully you're hearing that. And it doesn't matter if I hit it on my head, it's going to be the same note. Some of you might be paying really close attention, and you might also be hearing an additional note. So I'm going to hit this on something hard like the table. You hear that higher note? And then there's also this lower note. So I'll show you where the microphone was. So that's interesting. There's 2 notes. And you can play with this when you're in my classroom, and I'll show you. But there's that. And that. And if you're musically inclined, I know you're thinking, oh, that's a major fifth. And that's right. So and these 2 notes are D and A. So there you go. So this thing actually has 2 natural frequencies. Some things have no natural frequency. When I hit the table, that's not a note. That's not vibrating at some frequency. So some things do not have a natural frequency. Other things do have a natural frequency, like if you hit a water glass. Some things, like this tuning fork, have two natural frequencies. And so I just want you to know that vocabulary, natural frequency, that means the frequency that it vibrates at when you get it going. And then some things have two. When things have multiple natural frequencies, we call the lowest one the fundamental frequency. The lowest one is the fundamental frequency. And then the higher one, or one or ones, higher one or ones, overtone is an overtone, or they are overtones. So I told you there's a low-pitched hum. I keep looking for something that looks like a microphone. Anyway, the low-pitched hum and the high-pitched ding. That's the high one, but there's also this okay, and like I said, I hope you can hear that. And if not, we'll play with it in the classroom. That's all for today. I hope you have a great day. And remember, don't break the laws of physics.